surds are a way to calculate with irrational numbers. So let's have a look at these numbers. We've got root 7. Now, if you type root 7 into your calculator, you're going to get 2.64575 and then that number is going to continue depending on how many spaces on your calculator display. But that's a rational number and it's going to go on forever. Then we can have a look at the 13. So 13, root 13 will give us 3.6055512 and again that number is going to continue. Now look at the question. This is a multiplication. So what happens when we times these two numbers together? So you can use those decimals, or we can just type root 7 multiplied by root 13 into our calculator, and we're going to get 9.53939201. And again, that'll be an irrational number, and there'll be an infinite number of decimal places with no pattern to those decimal places. So what we have here, it does look like a bit of a mess. Is there an easier way? And there is. When we do root 7 multiplied by root 13, that's the same as saying the square root of 7 times 13 altogether. Now, 7 times 13 gives us 91. So it's a square root of 91. Now, what happens when you type the square root of 91 into your calculator? Well, you get 9.53939201, and the number continues. So we're getting the same number as what we got when we actually calculated the full decimal for those surds. Rather than writing down all these, millions and millions of decimal places that we might potentially need, we can just leave them as a surd. We can leave them as a number with a square root. So root 91 uses 3 characters. We've got the root symbol, the 9, and the 1. We're using 3 characters to represent it. When we write down the full decimal, the one I've got here has got 8 decimal places. We've got the decimal place and the 9, that's 10 characters. And I've got the dots on the end, and I will include those because they tell us it's a rational number and it continues on forever. So I've used 13 characters to show it to 8 decimal places of accuracy. Now, what accuracy do I have for root 91? Well, we have the full amount of accuracy. We haven't had to round it off. We haven't had to cut anything off. Root 91 is the full number. So when we talk about doing the calculation of surds, what we're talking about is being accurate, not rounding, keeping the full value of the number. Because what happens very often is that later on you do some cancelling out and it stops being a surd and you can get a whole number answer out of it. But if you rounded earlier on, then you kind of put in jeopardy that you don't get those whole numbers because you already cut off some of the numbers. For our next example, we've got 7 lots of root 17 and we've got 5 lots of root 17. So altogether, that means we've got 7 plus 5 is 12 lots of root 17. So all I've done is added up the 7 and the 5 to get the 12, and then I'm just counting how many root 17s we've got. So you can also count surd characters like root 17 as an algebra letter. If it was 7x plus 5x, then this would be the same rule. It would be 12x. So it works the same way. Now, you could calculate this and see if it actually works. So if we have 7 lots, so 7 times root 17, that's going to give us 28.861739.3, and again, that number continues. And we're adding it to 5 lots of root 17, so 5 times root 17, which gives us 20.6155281, and that number continues on. So we add these together, what you should get is the same as 12 multiplied by root 17. So it should be giving you 49.47726775, and then that number continues. So again, look at the difference between the 2 sets of calculations. 7 root 17 plus 5 root 17 equals 12 root 17. It only takes up, about a third of the screen. It doesn't really use a lot of numbers. Now let's have a look at the decimal version. It takes up nearly the full screen. I've had to round it off. Some calculators will give you more numbers than this, and it's not going to be accurate because I've cut off some of the numbers to be able to write it down on the page. So I'm not going to go through this again. This is not correct. We are not going to be writing out the full decimals. It's not accurate. They've been rounded off. From now on, I'm only going to be talking about surd calculations and leaving the root in so we have our full level of accuracy. Now, if for some reason you need to know the value of 12 root 17, You can type it into your calculator and you can get the 49.47 out of it. So, it's not that we're never going to be using that is, just over 49. It's just easier to write it down as a 12 root 17 than write it as a decimal. Sometimes you get a surd to simplify, and it looks like it's already simplified. We've got root 27. What can we do with root 27? Well, we can exploit the first thing we did kind of backwards, where we said that, and we'll write down a little rule for this. If you have the root of A and you multiply it by the root of B, that's equal to the root of A times B. So this can work backwards. So our root 27 takes the place of our root A times B. So we need to split 27 up into two factors. There's going to be A and B. Now, often there's lots of different ways to do this. And what we're looking for is a particular kind of number. We're looking for a square number. 27 is the same as 9 times 3. So root 27 is the same as root 9 times root 3. Now, why have I chosen those numbers in particular? 9 is a special kind of number. It's a square number. And we can actually work out the square root of 9. The square root of 9 is 3. So we can see that 27 is equal to root 9 times 3, which is equal to root 9 times root 3. Root 9 is 3. And so we can write our answer as 3 lots of root 3. So what we're trying to do is kind of make the root part of this much smaller. The key to it is that root 3 is a surd. It is an irrational number. The decimal places have no pattern and they're going to have no end. Root 9 is not a surd. There is a pattern to it in effect because it's just it's a whole number. So whole numbers aren't surds. Now, why is 3 root 3 better than root 27? Well, it might be, people who work with surds, they probably memorise what root 3 is. They probably haven't memorised what root 27 is. So making it into smaller surds just generally makes things easier to work with. Makes it more understandable for people who use these things. So look at the next question. We've got root 8 times root 6. So we know that's going to be equal to root 8 times 6. And 8 times 6 is 48. So you might think, great, I've simplified it. However, with that 48, you're always going to think, can I divide this by a square number? Is there a square number that divides into 48? So think about your square numbers. So the smallest one that's going to be relevant to us is 4, because we can divide everything by 1, and that's not going to make any changes for us. Can we divide it by 4? And we can. Root 48 is to be equal to root 4 times 12, because 4 times 12 is 48. That then, therefore, is going to be equal to root 4 times root 12. And root 4 being a square number, root 4 is 2. So that gives us 2 lots of root 12. Now again, you might think, okay, great job. I've simplified it. I have a smaller surd. I've gone from 48 down to 12. Then think about the 12. Can you split 12 up like this as well? And you can. 12 can be split up into root 3 times root 4. And again, it's split up into another 4. And root 4 is equal to 2. So we can go a little bit further with this. Now, rather than continue from this point, what we could have done is when we looked at the 48, we could think about the largest square number that divides into it. Now, 4 does, but is there a larger one? So what's after 4? Well, 9 is a third square number. So what's 48 divided by 9? Well, that gives us 5 1/3. So 9's not going to work. What's the next one? 16. What's 48 divided by 16? And it's 3. So that's a whole number, so we can use it. So it would have been better to say that 48 is equal to the square root of 16 times 3, equal to root 16 times root 3, and root 16 is 4. That gives us 4 root 3. And you think, out of those two answers, which one is the best? 4 root 3 is the best one because that's a smaller surd. Root 3 is smaller than root 12. They're both accurate, they're both surds, they're both correct answers, but the 4 root 3 is more simplified. Now, what happens if you do make this mistake? Well, as I said, when you've got the 2 lots of root 12, you can turn root 12 into root 4 times 3. That would be 2 times root 4 times root 3. Root 4 is 2. That gives you 2 times root 3. And then 2 times 2 is 4, giving you 4 root 3. So if you do make a mistake and you divide by not the highest common factor in terms of square numbers, you do a smaller one. As long as you check your new surd and think, can I divide that down as well? You can always do it in 2 steps, like I've shown you in purple here, and you'll get the same answer. Of course, doing it that way is twice as much work. So always try and divide by the largest square number that you can. Moving on to our next question, we've got a fraction. Now, we've already discussed some surd rules. So if we could say that a times b is equal to ab, then we can say that the root of a times the root of b is equal to the square root of a times b. We do the same thing with division. So if you've got a divided by b, you can write it as a fraction a over b. The same thing works with roots. If you've got root a divided by root b, that's the same as the square root of a over b as a fraction. So when we've got 264 roots divided by the root of 6, we can say that's equal to the square root of 264 over 6. Now we've got the square root over the way and we've got the fraction bit all together. We can simplify that fraction. So we can do 264 divided by 6. It's not a calculator paper, you have to use a written method to do this, so you can use your calculator if it's a calculator paper. But 264 divided by 6 is 44, so that gives us root 44 as our initial answer. Now, we don't have to finish there, because with root 44, you've got to think to yourself, can I divide this by a square number? So think about your square numbers. Again, dividing by 1 will give you 1 times 44. That's not going to help us. We've still got the 44 there. What's the next square number? Well, 4. Can we divide it by 4? And we can. So root 44 is equal to root 4 times 11. That's the same as root 4 times root 11, and root 4 is 2. That gives us 2 lots of root 11. Before you move on, just think to yourself, well, can I divide 11 down any further? Now, 11's a prime number. That means that we can't. But if it's not a prime number, just think to yourself, well, can I divide it by 4? Can I divide it by 9? Is there anything else I can do with this? The last thing to mention is that these kind of Surds rules don't work with addition or subtraction. So you've got a minus b. That's not going to be the same as root a take away root b to give you root a minus b. It's not going to work that way. So this isn't a rule we can use. Now, we did look at one with addition, but the way that addition works is if you've got a root, let's say n, so we've got root n, and we've got another root n, and these got coefficients on them. Let's say we've got a lots of root n and b lots of root n, and we add them together. You can add together the a plus b, then it's all out of root n. So again, that's the example we talked about. You can kind of use this like algebra. So if you had a lots of x plus b lots of x, then you would have a plus b lots of x. Just be careful that multiplication and division works like it will with normal numbers, but addition and subtraction is going to work more like with algebra rules. The next thing to look at with Surds is quadratic equations, and unfortunately you can have quadratic equations that include Surds. So let's have a look at how they work. So we've got 4 plus root 7 multiplied by 4 plus root 7. So you proceed like you would normally with quadratic equations. We're going to do 4 times 4 is 16. 4 times root 7 will give us 4 lots of root 7. Then we do root 7 times 4, which again is going to be 4 lots of root 7. And then this is the interesting one. We do root 7 multiplied by root 7. So what's that going to give us? Well, root 7 times root 7 is equal to the root of 7 times 7. 7 times 7 is 49. And we can do the square root of 49. 49 is a square number. It gives us 7. What this shows is if you multiply a surd by itself, then the square symbol disappears. Root 7 squared is 7. And effectively, if you square a root, those are opposite inverse operations and they cancel out. So we have plus 7 on the end. Now, in quadratic equations, we always have it where we can simplify bits. So we always have 2 middle terms that we can add together. It works the same way as with algebra. So if you've got 4 lots of root 7 plus another 4 lots of root 7, that's going to give you 8 lots of root 7. What changes here is we also have 2 whole numbers. We've got 16 and we've got 7. And 16 plus 7 is going to give us 23. So our final answer is 23 plus 8 lots of root 7. So it works exactly the same way as with a quadratic. It's just rather than doing x times x is x squared, you'll have a surd multiplied by itself, which will give you a whole number, and you can add that on to the other whole number. So we only end up with 2 terms at the end once we simplify, rather than the 3 that you normally get with quadratics. So now we're going to have a look at some examples of quadratics. 5 minus root 3 multiplied by 3 plus root 3. So multiply it out. 5 times 3 is 15. 5 times root 3 is 5 root 3. Negative root 3 times 3 is negative 3 root 3. So be really careful with negative numbers. Negative numbers belong with the term after it. So that negative belongs with the root 3. And then we're going to do negative root 3 times positive root 3. So if you times the root by itself, you're squaring it, you're cancelling out the root symbol. So we're going to get 3. The difference with this one is it's a positive times a negative. So it's going to be a negative 3 altogether. The last thing to do is to simplify. So look at your normal numbers first. We've got 15 and negative 3. 15 take away 3 is 12. Then we look at our surds. We've got 5 lots of root 3. Take away 3 lots of root 3. Altogether, that'll be 2 lots of root 3. And so now we have 2 terms for our final answer. Looking at another quadratic surd, we've got 3 take away root 45 and 5 take away root 45. So again, we multiply it out. 3 times 5 is 15. 3 times negative 45. Again, there's negative symbols belong with the term after it. That's going to give us negative 3 lots of root 45. Then we have negative 45 times 5. That's negative 5 lots of root 45. And then negative root 45 times negative root 45. Negative times negative is positive, and a root multiplied by itself will cancel out the root. We collect together the number terms. 15 plus 45 is 60. And we collect together the surds. Take away 3 root 45, take away 5 root 45, that's a negative 8 root 45. Now you might think that you've done there, but you might notice the 45 is quite a large surd. And particularly with the larger surds, there's always a chance you can divide them by something. And 45 is in the 9 times table. So we can simplify this further. So we're going to have 60 take away 8 lots of root. If we divide it by 9, we get 5. So 8 lots of root 9 times 5, which of course we can write as root 9, root 5. And we know what root 9 is. Root 9 is 3. So we have 60, take away 8. We can do 8 times 3. That's going to give us 24. So our final answer is 60, take away 24 lots of root 5. So no matter what kind of surds question you're doing, when you get to your final answer, always just think to yourself, this final answer of this surd, can I divide it by a square number? And if you can divide it by a square number, then you can simplify it further. Our next example is 4 plus 5 lots of root 27. Again, it's a larger surd. There's probably going to be some simplification at the end. And multiply it by 4 lots, take away 3 root 27. So again, multiply it out. 4 times 4 is 16. 4 times negative 3 is negative 12 with a root 27 on it. 5 times 4 is 20. Again, that has a root 27. And then we've got 5 lots of root 27 multiplied by negative 3 lots of root 27. So do the whole numbers first here. 5 times negative 3 will give us negative 15. Then root 27 times root 27. We know if we times it by itself, we cancel out the root. It's just going to be 27. But how does it interact with the 15? Well, the 15 is to be multiplied by the 27. So all of this is actually going to be together. So when we simplify our whole numbers, we've got the 16, but we're taking away from it 15 multiplied by 27, which will give us negative 389. Then we have a look at our surds. Negative 12 plus 20 will give us 8. It'll be plus 8 lots of root 27. There's a few more things to simplify this. So the first thing is the root 27, we can divide that by 9. So negative 389 plus 8 lots of root 9 times root 3, because 9 times 3 is 27. And we can do root 9, it's 3. So negative 389 plus 8 times 3 is 24. So that's going to be 24 root 3. One more way you can simplify this is swapping the two terms around, because if you put a positive at the start, you don't need to write the positive symbol. We assume positives at the start are positive, if you've got a symbol or not. Then we take away the 389. So write it that way around, just means we're using one less character, so it's a little bit simpler, but not usually necessary. Now, the next question has got some quite large surds in the quadratic, and all the surds are different. Now, what you might want to do first is simplify the surds before you start. So, for example, root 27 is the same as root 9 root 3, which is 3 root 3. And root 63, that one can also be divided by 9, so that's going to be root 9 root 7, which is going to be 3 root 7. Now that I've simplified those surds, you'll see we've got root 3 and root 7, which we also have in the first bracket. This is going to make things a little bit easier for us. Now, write out the question. We've got our 8 lots of root 3, that's fine. Take away 4 lots of root 7. When I write 7 lots of root 27, that's 7 lots of, and root 27 is the same as 3 root 3. Now we can do 7 times 3, it's 21. So it's better written as 21 root 3. Then we added on the 5 lots of root 63. Root 63 is 3 lots of root 7. 5 times 3 gives us the 15. And then we have the root 7. So all I've done is I've multiplied my simplified surds by the number on the front. So now we can multiply our brackets. 8 root 3 times 21 root 3. So we're going to have 8 times 21, which is 168. And then root 3 times root 3 is 3. So we've got a whole number part, it gives us 168. And we've got a surd part that gives us 3. Altogether, that's 504. Next, we have 8 lots of root 3 multiplied by 15 lots of root 7. So again, it would be the whole numbers first. 8 times 15 gives us 120. And then root 3 times root 7 will give us root 21. Next, we're going to do negative 4 root 7 times 21 root 3. So negative 4 times 21 is going to give us negative 84. And root 7 times root 3 is root 21 again. Then for our final section, look at the whole numbers first. Negative 4 multiplied by 15 is going to give us negative 60. And then root 7 times root 7 will give us 7. So we have 60 times 7. So we can do 60 times 7. That's going to give us negative 420. And we can simplify the two middle terms. 120 lots of root 21 take away 84 lots of root 21 will give us 36 lots of root 21. Now, even after those simplifications, we still have 2 lots of whole numbers. So 504 take away 420 gives us 84. So our final answer is going to be 84 lots of 36 lots of root 21. At the end, again, just think, right, can I divide 21 through by anything? You can divide it by 7 or 3. Neither of those are square numbers, so you can't actually simplify root 21 any further. So that's our final answer. You see, with this question, there's quite a lot of complicated things going on, so always make sure when you multiply 2 surds together, you can multiply the surd terms, but any coefficients, any numbers at the front, they get multiplied together separately. Then just take note of all the simplifications we've got and make sure you simplify each step one at a time, not trying to do too much at once, just so you don't miss anything out. The key thing here was spotting that we had some large surds at the start and simplifying them in the initial question saved us some headaches later on. The next thing we'll look at is something called rationalizing the denominator. Now, I've already gone through one detail with surds, which is with surds, we want the smallest surd possible. Now, another detail with surds is that we want no surd on the denominator. And again, this is just a thing that makes surds easier to work with. So you can see with our question here, we've got 8 over root 11. The denominator is a surd. So we need to try and fix that somehow. Now, the way we fix that is we take our fraction, 8 over root 11, and we already know a way where we can get rid of a surd. And it's when you multiply it by itself. If you square a surd, then the square and the root cancel out. So when we take 8 over root 11, what we can do is take the root 11 and multiply it by root 11. And if we do root 11 times root 11, we're going to get 11 on our denominator because we multiplied it by itself. Now, doing this, we're working with equivalent fractions. So if we multiply the denominator by 11, we also need to multiply the numerator by 11 as well. And 8 times root 11 is 8 lots over root 11. There's not really anything we can do to simplify that. And so we get 8 lots of root 11 over 11. Now you might be asking yourself, well, how is that simple in 8 over root 11? So again, it's a detail with surds where we want to try and simplify it in this way because it's easier to work with. We then use it for other things. Another thing you can do with this is we can actually divide this by 11. 8 lots of root 11 divided by 11 gives you 8/11 root 11. And now we've actually got the surd out of the fraction altogether and just had the fraction out at the front as a coefficient, as a number at the front. So we're going to practice rationalizing the denominator. So this question here, the denominator is root 11. So we want to get rid of that. So the numerator is 33 plus 7 lots of root 11. The denominator is root 11. So to make the denominator into a whole number, we need to multiply the surd by itself. But if we multiply the denominator by root 11, we also need to multiply the numerator by root 11. And by saying multiply the numerator, that's the entire numerator. So it's got two terms, like in this question, both terms have to be multiplied by root 11. In the previous question, there's only one term to multiply, but this one's got two. So let's multiply everything by root 11. 33 times root 11 is 33 root 11. 7 lots of root 11 multiplied by root 11 gives us 7 times root 11 times root 11. Now, again, we're multiplying root 11 by itself. So root 11 times root 11 is 11. The square and the root have cancelled themselves out. So we've got 7 times root 11. And then on the denominator, we've got root 11 times root 11, which again is going to cancel out to give us 11. All we're going to do now is use 7 times 11, which is 77. So altogether, that's going to give us 33 root 11 plus 77 all over 11. And what we can actually do now is we can actually divide this by 11. So 33 divided by 11 is 3. That gives us 3 lots of root 11. And 77 divided by 11 is 7. That gives us 7. So now we've gotten rid of the fraction altogether. And now for this one, you can really see the effect of this. It's really simplified it down to something that's much, much simpler, but represents the same number. 33 plus 7 root 11, all divided by root 11, is the same number as 3 lots of root 11 plus 7. So a big objective usually with this is to try and actually divide by the denominator to get rid of the fraction altogether. So let's try and rationalise another example. So we've got 12 take away 9 lots of root 3, all divided by root 3. So to rationalise this, what we're going to have to do is multiply the denominator by root 3. But then we'd also need to multiply the numerator by root 3 as well. And again, both terms of the numerator. 12 times root 3 is 12 root 3. 9 root 3 times root 3 gives us 9 times root 3 times root 3. We're multiplying root 3 by itself. That's going to give us 3. So it would actually be 9 times 3. All divided by root 3 times root 3 is 3. So it looks like our final answer is 12 root 3 take away 9 times 3 is 27, all divided by 3. But again, we can divide this by 3. 12 divided by 3 is 4, and 27 divided by 3 is 9. So our final answer is 4 lots of root 3 take away 9. Now, our next question looks like the previous question. So we've got 7 over 10 minus root 11. So what you might want to do here is multiply through by root 11, the numerator and the denominator. It would have to be both parts of the denominator you multiply by root 11. Now, if we did this, we would get 7 lots of root 11 for the numerator. That looks fine. But for the denominator, 10 times root 11 is 10 lots of root 11. And then root 11 times 11 is 11. Now, by multiplying through by root 11, what's happened is we still have root 11 on the denominator. It has shifted from the second term to the first term. So this hasn't helped us. So what can we do? This method's not going to work. Well, we can use a little quirk of quadratics where certain quadratics cancel out some of the terms you get. And so what we're going to multiply by here is the opposite of the denominator in effect, which is going to be 10 plus root 11. And we multiply the denominator by 10 plus root 11. We also need to multiply the numerator by 10 plus root 11. So let's see how this works out. So let's do the numerator first. 7 times 10 is 70, and 7 times root 11 is 7 root 11. So the numerator looks fine. Now for the denominator. So we have a quadratic to multiply out. So 10 times 10 will give us 100. 10 times root 11 will give us 10 root 11. Negative root 11 times 10 will give us negative 10 root 11. And then root 11 times root 11 will give us 11. It's positive and negative, so that'll be negative altogether. So we get something like this. Now, the reason why we multiplied by the same denominator, but we flip the signs, is because if you flip the signs, have a positive and negative. When you cancel out the middle two terms, as you can see here, we've got a positive 10 root 11 and a negative 10 root 11. And they cancel out to give us 0. So the third term on the denominator has cancelled itself out. It's gone. And that's what we wanted. So now our numerator is still 70 plus 7 lots of root 11, but our denominator is 100 take away 11, which is 89. And we can write that as our final answer, potentially. If you really wanted to, you could divide by 89 and we could have 70 divided by 89 plus 70 over 89 root 11. Can we cancel the fractions? 89 doesn't divide through by 7, so we can't cancel that one. 70 over 89, we could change that into a mixed number perhaps. But as you can see, trying to divide by 89 doesn't necessarily make this simpler. So what we're probably going to do is keep the fraction as our final answer and not necessarily simplify it in that way. Again, it's not incorrect, it's just more complicated to try and divide through by 89. So only can I save dividing through by the denominator in case, so it will make it simpler. So we'll look at one more example of rationalising the denominator using quadratics. So our numerator is 4 minus root 2 and our denominator is 2 minus root 2. We are rationalising the denominator, so we need to multiply it by a version of itself to cancel out the root. So that's going to be 2 and root 2, but remember the sign has to be opposite. If they're both negative, you get a big negative number. If they're both positive, you get a big positive number. But if you have an alternate, positive and negative, doesn't matter which way around they are, then you'll cancel out the root and get a 0. Of course, we multiply the denominator by 2 plus root 2. The numerator also needs to be multiplied by 2 plus root 2. And since the numerator also has 2 terms, this will be another quadratic to multiply out. So we have 2 quadratics in one. So multiplying this out, 4 times 2 for the numerator is 8, and 4 times root 2 is 4 root 2. Then negative root 2 times root 2 is negative 2 root 2, and negative root 2 times positive root 2 is 2. Then we do the denominator. 2 times 2 is 4. 2 times root 2 is 2 root 2. Negative root 2 times 2 is negative 2 root 2. And then negative root 2 times a positive root 2 is a negative 2. So once we have our 2 quadratics, we have to simplify best we can. So for the numerator, look at your whole numbers first. For whole numbers, we have 8 and we have 2. It's a positive 2. Altogether, that gives us 10. Then we look at the roots. We've got positive 4 root 2 and negative 2 root 2. 4 take away 2 is 2. That's going to give us 2 root 2. Then we look at the denominator. Look at the whole numbers first. We've got 4 and we've got negative 2. 4 take away 2 is 2. Then we look at the roots. And what should happen here is we have a positive 2 root 2 and a negative 2 root 2, which gives us 0 lots of root 2. So there's no root to write down. So the only thing we have for the denominator is the 2. Now, if a fraction over 2, we can divide by 2. So if we take 10 plus 2 root 2 and divide it all by 2, you can divide the 10 by 2, and you can divide the 2 root 2 by 2. 10 divided by 2 is 5, and 2 root 2 divided by 2 is 1 root 2. So our final answer is 5.
Ouch! This is why in some videos I have explained scratches.